So we are looking at exercise 1 on page 95 in the workbook, and this is our first example of finding eigenvalues and eigenvectors for a linear operator that's going to have a bigger matrix than 2 by 2. Okay, so they'd like us to find the eigenvalues and a basis for each eigenspace for the linear transformation defined like this. Okay, so to get started, we need a matrix for this transformation, and usually the best choice of basis is just the standard basis, in this case for R3. Okay, and the standard basis is nice because we can kind of read off the matrix just by looking at the coefficients over here on the right-hand side. Okay, in other words, we're going to get a matrix that looks like this. Negative 2, 2, 2. There's the first row. Then 0, 2, 4. There's the second row, and then 0, 2, 0. And again, those numbers are just coming from looking directly at the coefficients, okay, on the right-hand side of our equation. Okay, and that's the matrix of our transformation relative to beta. We're going to try to find the eigenvalues of that matrix to get the ball rolling here. Okay, which means that we need to take a determinant. Okay, so we're going to take A minus lambda, which again, remember, just is taking our starting matrix and subtracting lambda from each of the main diagonal entries. Okay, and then we need to take the determinant of that 3 by 3. Okay, and we talked about this in the last chapter. All right, in this case, probably easiest to take our determinant by expanding along that first column because we've got 2 zeros there. All right, so we are going to get, starting with the negative 2 minus lambda, we're going to get that number multiplied by the determinant of the 2 by 2 that we get by crossing out the row in the column that 2 minus lambda is in. Okay, you might remember this process from the last chapter. Okay, so what's left over then is just the 2 by 2 matrix that looks like this. Okay, and to complete that calculation, we just need to take negative 2 minus lambda. I'm actually going to factor that, pull out a negative sign. And then we're going to multiply that by the determinant of this 2 by 2 that's left over. Okay, so that's going to be 2 minus lambda times negative lambda minus 2 times 4 is 8. Okay, and we'll need to do a little bit of algebra here, so let's see. Moving to the next line, we've got negative 2 plus lambda. We'll go ahead and kind of multiply out what we're seeing inside the parentheses there. So that's going to be negative 2 lambda plus lambda squared minus 8. Okay, and if you look at that part that's in parentheses here, that actually factors. Okay, you can double check my work here. Lambda squared minus 2 lambda minus 8 factors as lambda plus 2 times lambda minus 4. Okay, so we can actually do a little bit better than this. Notice that these two factors are repeated, so we could write this as minus lambda plus 2 squared times lambda minus 4. Okay, and from that, you can probably see what our eigenvalues are going to be. One of them is going to be negative 2 and the other one's going to be 4, because that's what we would get if we solved this equation by setting it equal to 0. All right, so let's look at those two eigenvalues one at a time here. We'll start with the positive one, lambda 1 equals 4. Okay, and the idea again is we need to solve a system of equations. Okay, so we're going to go back up to our matrix at the top here, and we need to plug in lambda equals 4 for each of the lambdas that you see. All right, so imagine putting a 4 in place of all of those lambdas. In the upper left-hand corner, we're going to get minus 2 minus 4 is negative 6. Okay, other entries are going to be the same. Okay, and then for the second row, 0, and then 2 minus 4 is negative 2. Okay, and finally the third row is 0, 2, and minus lambda would be minus 4. Okay, that's the system that we need to solve. Okay, so we would do row reduction. Okay, you can either do this by hand or on a calculator. I'm just going to show you what winds up happening here. Okay, there's our reduced system after we do row operations, and notice that there are two pivot positions. So we have one free variable, looks like it's x3 in this case. All right, so over here to the right, let's give that free variable a name. Okay, and I'm trusting that by now you know how to solve a system. Okay, so you can look at the second equation and see that x2 is going to actually be 2 times x3, which would be 2t. And you could go back to the first equation and solve for x1. That's going to take a little algebra. You'll probably have to write this out yourself, but x1 should turn out to be t when you do that. Okay, and since there's just one free variable, that means there should be one linearly independent associated eigenvector here. Okay, and we can just give the free variable any non-zero value we care to. T equals 1 is nice in this case. That's going to give us the vector 1, 2, 1, if you look over here at our solution. Okay, or in terms of a basis for the eigenspace, we could write that as beta 1 is just the single vector 1, 2, 1. Okay, that forms a nice basis for our eigenspace, okay, which is part of our answer. All right, so in words, that would be the basis for the lambda equals 4 eigenspace. We'll use that terminology. Okay, and now we just need to repeat that same calculation, this time for the other eigenvalue, which was -2. Okay, same steps that we just went through. We need to go back to our original matrix up here at the top of the page, and this time plug in -2 for all of our lambdas. Okay, and if you do that, here's the matrix that you're going to end up with. Okay, we're setting all of that equal to 0. There's the system of equations that we need to solve. And if you do row operations this time, you are going to get a bunch of zeros. So we could look at that system and ask, where are the pivot positions? I actually only see one of them in this case. That's the only first entry of a row that's non-zero. So we actually have two free variables in this case, x1 and x3. Okay, so I'm going to make x3t and x1u. Those are our free variables. And if you then solve for x2 using that first equation up here, you're just going to get x2 equals -x3, which is going to give you a -t. All right, well, this time we have two free variables, which means we should actually be able to come up with two linearly independent eigenvectors associated with this eigenvalue. Here's where that algorithm comes into play that we described in the previous video. Okay, so if we follow that algorithm, the idea is to take the free variables one at a time and give them non-zero values. Okay, so let's start with t. If we let t equal 1 and all of the other free variables be 0, okay, which in this case would be u, that's the only other one, we're asking what eigenvector would that generate for us? Okay, well, we can answer that question just by looking up at our solution form here. If you plug in t equals 1 and u equals 0, you're just going to get 0, -1, 1. There's the resulting eigenvector. Okay, and now we're going to do it the other way around. So we're going to let u be 1 and all of the other free variables be 0. That's basically just flipping the 0 and the 1, and that's going to generate a second linearly independent eigenvector for us. Okay, this time t is 0 and u is 1, so we're just going to get 1, 0, 0, it looks like. Okay, and that generates a basis for the eigenspace associated with -2. This time it's going to contain two vectors. And so, like we did in the previous example, I'd like to do one more step here. Okay, if I can get this to scroll, where we just kind of summarize our answers here just by making a table. You don't necessarily have to do this, but sometimes it helps you just to see kind of at a glance everything that we did. So we'll make a column for our eigenvalues lambda, and then a basis for the eigenspace. I sometimes like to use the notation E lambda. Okay, that just means eigenspace associated with the eigenvalue lambda. We had two eigenvalues, one of them was 4, and if you look up at our work, the basis that we came up with was 1, 2, 1. Okay, and then similarly for -2, we came up with a basis that had two vectors, and they looked like this.